So independent and dependent events, we just had a discussion before making the connection with mathematics and probability. An independent event is when the outcome of an event does not influence the outcome of a second event. And this is how it is in symbols. We have the probability of A and B happening. And we've done this one before. We've done this one when we rolled the die twice, right? Or rolled a pair of dice. And we found out that it was 1 in 36 chance of something happening, or depending on the primes, and we were going through there. So we found that out by doing, you do not have to write this. Oops, I just did the wrong screen. I know it. So we did, if we wanted to roll a 2 and then a 2, there's a 1 in 6 chance that we rolled a 2, and we multiplied that by 1 in 6 chance of getting a 2, and it became out to be 1 in 36, just to remind you, because we're going to be referring to that. Okay? But then there is dependent events. Dependent events are the outcome of one event. It affects, so there's influence, the outcome of a second event. Okay? For example, if the Panthers didn't win on Sunday, okay? If the Panthers didn't win on Sunday, they had things going on where there was probability of going to the Super Bowl. Okay? And if they didn't win Sunday, their probability of going to the Super Bowl, let alone winning, would be 0. Am I right? So that would be a dependent variable. You had to win the conference title in order to get to the Super Bowl. Or for those of you that don't care about football, if you wanted to... No, I don't have a concise response like that. I don't have it as a response but we'll get to those. And the way that we do that in symbols is we have the probability of A and B happening whenever it's a dependent variable, when it relies on it, the same way that you will be filed by your guardians as a dependent, so they get a little bit of a tax cut because of how much they have to pay to feed you, shelter you, all that stuff, put up with you, right? And that's the probability. No, not your sister is probably not unless your sister is your guardian. Your probability of A times the probability of B following A. B following A. Some of my hair. Let's do some examples. And when we're doing these examples, I want you to remember that this is what the probability is. The number of ways of an outcome can occur over the total number of possible outcomes. That's something that you need to have memorized already. That's something that will come up on the test. Did you write that? Good. Probability is the number of ways an outcome can occur over the number of possible outcomes. So, in a popular board game, I don't know why it's not named, you go to jail if you roll 3 doubles in a row. What is the probability of rolling 3 doubles in a row? So there's 3 things that are happening. There are 3 things that are happening here, so we are going to find the probability of those 3 things happening. And the question I ask you, if I roll 1 double, does that change anything about rolling a second double? Here's the way that it would be. For example, if you roll a double 1, you can't roll a double 1 anymore. That would be a dependent. But this is independent. So let's do the probability of rolling a double. And I'm going to call it double 1. There's going to be an apostrophe up top there. Double 1. Am I recording? Okay. Double 1. So what is the probability of rolling a double? How many doubles can you get by rolling a die twice? Yes?
It's like over 36.
No.
It's over 12.
Yes.
6?
There are 6 of them. You can get a double 1, double 2, double 3, double 4, double 5, double 6. Okay? So there are 6 out of how many total that we did just a minute ago? 36 possibilities in all. And I need to simplify that. Then I have the probability of rolling a double for the second time. Does that change anything? No, it's still 6. And once again, the probability of getting a double a third time, once again, is 6. So we're asking, what's the probability of messing around and getting a triple double? Huh. And according to our formula right here, we have to multiply each probability together. So I just do 1 times 6, 1 times 6, 1 times 6. Or sorry, 1/6, 1/6, 1/6. So in order to do that, I'm just going to rewrite it so it's nice and pretty for the camera. So 6 times 6 is 36, times 6 is what? 216. Do I agree with you? Yep. So it's 1 over 216. So the probability of getting a double 3 times is 1 in 216. And there's a lot of writing here, so I'm going to go ahead and circle that so Mr. Smith knows exactly what I was trying to answer. Because Mr. Smith gets confused easily. Now for this next one, I wrote that way too big. For this next one, I'm going to do the work above it so I can keep this onto one page for print-off reasons. Oh, and by the way, guys, when you're printing up these notes, I use a whole bunch of different colors. Save yourself some money and just do print and gray style. Okay, I've seen some really pretty looking printouts of this that you guys have used your color printer, but ink's super expensive, or at least ask your parents if you're using color. All right, I'm going to use the area above the question to answer this one. So, bag lunches are prepared for 50 students on a field trip. There are 3 different desserts in the bags. 20 contain a brownie. 15 contain a chocolate chip cookie. And 15 contain my favorite, an oatmeal raisin cookie. The bags are arranged in random order. Connie and Steve were the first and second in line. What is the probability that Connie and Steve both select a bag containing a chocolate chip cookie? Now, as far as your guys' page goes, here's how I want you to do it. Your page, I want you to draw a line right there, and then this is going to be your workspace all through here. But I'm not going to use that because I want to leave plenty of room so it's visible. Yes, ma'am. Yep, that's exactly the room I'm using. Yep, that's the exact spot that I'm using. So you can use the bottom front of this if you want. This will be visible. This will be visible. So we have, well, can someone tell me, is this another dependent or is it an independent situation, and why? What do you think? Independent? Dependent. Why do you think it's dependent?
Because once
We're going to do ladies first. We're going to have ladies go first. There you go.
one at lunch, then Steve will have less lunches to choose from.
Good. There it is. Once Connie goes through the line, there's going to be one less bag there. And in this situation, Connie is going to get one of those chocolate chip bags. So that means that the number of outcomes to get chocolate chip reduces, and the number of total outcomes reduces. You following me, sleepyheads? Okay, I would love to find that medium ground of you guys being like super energetic and then just the look that you guys are doing, because I don't even know if you're with me. And Avery's falling asleep. Yeah.
My first grade teacher
Yeah, I've had kids in class stand next to the desk. So we're going to find the probability first of Connie, since we're being nice, gentlemen, of Connie going first in the line. So the probability of Connie chip. I'm going to call it a Connie chip. If you don't know what that means, you should write Connie chocolate chip. Yeah, somehow your desk, Quinn, got moved to the right. Could you shift so it's more in front of Maggie's? A little bit more. I just need somebody to be able to get through there if there's a fire. You'd think that somebody would obviously be able to get through there, but keep in mind that in emergency situations, people aren't thinking clearly, especially in a group. There's been studies. Okay, the Connie chip. So the number of outcomes. What's the probability of how many times is she going to get that chip possibly? What are the number of outcomes for it? Yes.
15.
15, because there are 15 chocolate chip bags with a chocolate chip cookie in there. There are 15 bags with a chocolate chip cookie in there. That's from right here. How many bags are there in total? Wait, actually, yes. 50. There are 50. There are 50 bags when Connie walks up there and she's like, I want this one. Jake? I need to simplify this to 3/10. Always simplify. Always simplify. Always simplify. So now I'm going to find out the probability of Steve. So now we have one less chocolate chip, and we have one less bag. That does not look anything like I wrote.
Which side? Are you switching sides? You're on the other side.
I'm working on the one that we're talking about, bag lunches.
Yeah, but you're on the other side.
You working on this side?
The bottom line is you don't have anything except for this written.
Okay.
Why do you only have that written? What should you have written? Everything. That's right. So if your parents are curious as to how well you're following along in class, let alone doing the homework, they would be able to go and print out what I have, and yours had better look like that. Now we have one less chocolate chip and one less bag. So I have a different probability now for Steve. So the probability of a Steve and a chocolate chip. Steve with a chocolate chip cookie. Steve with the chocolate chip cookie. I've got how many possible successes is there? Fuller. 14 now, because there was 15, but Connie took it. They are friends. Steve wanted Connie to have it. Now, Connie already took her bag, so how many bags are left to take, Bella? 49. 49, and that could be and should be reduced 2/7. All right. I appreciate you guys' enthusiasm, but please, let's cut the chatter. I want you to chat with me. I know. I'm saying you're sitting in your desk. I didn't want you guys talking a whole bunch. I love the enthusiasm, but there's a halfway between this and running around the room. So we're done, right? No. We have to multiply the probability of event A and the probability of the event B after A happened. So I'm going to do that up here. So I have the probability of both chocolate. I'm going to write that elsewhere, more to the right. Oh. So I'm just going to put a line. No, not. So the probability of both chocolate chip. So I'm going to multiply 3/10 by 2/7. And if you're wondering where I'm getting that from, on the first page, it's this right here. Here's Connie's chocolate chip. Here's what's left over for Steve's chocolate chip. So I'm multiplying those two together, and I get 6 over 70, which can be reduced.
3 over 35.
It's 3 over 35. No, 2.
Over
Sorry.
3 over 35.
3 over 35. We okay over here? Can you leave the desks where they are, please? So probability of both getting a chocolate chip is 3 and 35.
That's a really low chance.
It is a low chance, but that's just the probability of it, right? Remember, probability is not odds. Probability is not odds. Yes, sir?
Is it just like the bags are random and you don't know which one has?
Exactly, yeah. It's just the brown paper bag, so you don't know which it is, and they were mixed around in the question as it says. Okay.
Like, what if the people are like really
Determine whether these are dependent or independent. When rolling a die and then spinning a spinner. Yes? Independent, you are correct. Ew. Independent. Those are all E's with one I. Drawing a marble from a bag and then drawing a second marble without replacing the first marble. Braden, what do you think? It's a 50-50 guess. If you're not feeling confident, that's okay. Dependent is correct. Dependent, and I'll show you exactly where that dependence happens. Without replacing. That's the biggest part right there. Without replacing, that means that there's going to be a different amount of things in the bag. Okay? Remember what I said at the beginning? There's always going to be some little bit of extra rule when it's dependent. It's going to be something that they're going to tell you to fill you in. As team captain, selecting someone to be on your basketball team, then selecting a second player. Yes? Dependent. Can you tell me why?
Because if you select someone first, then you can't select that first person to be your second person.
Yeah, exactly. They're already on your team, right? It's like, I know. I'm going to pick 5 Michael Jordans for my all-time basketball team. Yeah, that'll tell them. In a bag. Now, as we're doing this, keep in mind that what we're going to do is with each number, the bag resets. Okay? The bag resets with these. And on your homework, which is half of it, is very similar to this, we'll set that straight. In a bag, there are 5 red marbles, 2 green marbles, 4 yellow marbles, and 3 blue marbles. Once a marble is drawn, it is not replaced. Find the probability of each outcome. Okay? I could easily say that these all four of these are going to be dependent on each other, but they're only going to be dependent on the number itself. So you have 2 green marbles in a row. So I have the probability, so my event 1 is green 1. Green 1. My probability for the second one is green 2. the probability of drawing a green, I have 2 green marbles, and I have to think about how big of a sample area do I have. How many marbles are there in total? I need to know that. So the probability of green marble being drawn first is what? This is from last Tuesday? Yes. 1 out of 14. I'm going to add one more of that. Because there are 2 green marbles. 2 green marbles. Now with that one, see, you guys are already starting to see it. Right away, you recognize that there's only 1 green marble left in there, and there's only 13 marbles left. So we have 1 out of 13. So if I'm finding the probability of both green, I need to multiply those fractions together. 2/14, which simplifies to 1/7, right? 1/7. If I didn't simplify to 1/7, would I get the same answer?
Yes.
Yeah, I would just have to simplify later more. 1/7 multiplied by 1/13. And I know my math facts. 7 times 10 is 90, plus 21 is, 7 times 10 is 70, plus 21 is 1 out of a 91 probability. The probability of getting both green is 1. 91. Right?
Like you're colorblind. It's not gonna let you have that.
Now, we have probability of red and then yellow. So I have to do red. No, these are going to be independent of themselves. So the green marbles are put back in for this situation. Okay, the green marbles are put back in. So we have the probability of red, and we go up and we look and see how many reds do we have. 5 red marbles. So we have 5 red marbles out of the same 14 because we reset it when we went to the next situation. 5 out of 14, that doesn't simplify. So then I have the probability of the yellow. Now that there's only 13 marbles left, but there are 4 yellow marbles. Yes, sir?
So it says once a marble is drawn, it cannot be replaced. Does that only occur like once a problem, or are all these like connected?
That's why I've said it and clarified twice that each number is independent of the next number. Yes, ma'am?
Can we like cross 3 games then? Or
There would be if there's going to be. Yeah, this one wouldn't work like that either, though. But yes. So we got red, then yellow. I have to multiply those fractions together. 5 over 14. 4 over 13. I guess, yeah, you could, because it would be 5 over 7 and 2. Schneider?
would it, for the yellow, would it be 4 over 11 or 10? Because you pull out 5 red marbles and then you don't put them back in. So does
Oh,
that-
you're right. I'm sorry. I'm sorry. You're right. I'm wrong. Oh, wait, no. It's just 1 red marble.
Oh,
Yep, you had me freaking out for a second there because I was thinking about 14 times 13. So it's 10 out of 91. If you would have done cross simplification before, you could have made this 5/7 and that 2. Yeah. And that would be still 10 over 91. So I'm going to circle that. Moving along. How much time we got left? Beautiful. All right. a green and then a blue marble. So I remember my probability of green since I'm resetting. There are 2 green marbles out of 14. 2 green marbles out of 14. Then I want to get a blue marble. How many blue marbles do I have? There are 3 marbles, but then there would only be 13 left. Regardless of whether we're talking about marbles in a bag or spinners, that sort of thing, because spinners is on the homework in addition to stuff just like this, just keep in mind that it's however many are left for dependent variable, for dependent probability. So the probability of green and then blue is going to be 2/14 multiplied by 3/13. Come on. So what was that? 284 or 184? 182. Three over 91, and didn't we just do something that was times 3 to get 91? No.
Yeah, it's 91. Yeah.
Okay. So that one's 3 over 91. Now we're going to do a triple threat. Yes, ma'am.
Can we circle the whole equation?
Yeah, I would probably rewrite it. I'd probably rewrite it just so Mr. Smith knows what I'm doing, and I'd rewrite it like this. Like the green to blue is 3 over 91, and then I'd circle that. I would just have it nice and easy, but it's just reducing. Just reducing. Last one. A red marble, and then a green marble, and then a blue marble. The probability of a red marble is what? Joey? 5 out of 14. Then that red marble is not put back. We have then a green marble, which is 2 out of now 13. Then the probability of drawing a blue marble after that. How many blues are there? 3 out of just 12. So that means the probability of going red, green, blue is going to be 5/14, 2/13, 3/12, which is 1/4. So my numerator is going to be nice and easy. That's just 10. My denominator, however, I have to do 182 times 4. And since I can't use calculators in this class, that's right, 1632. Oops, dyslexia. 4. So I can reduce that by 2. So I have 728. I'm going to erase that because it's in my way. Red, green, blue. I'm going to reduce that by 2 to get 5,364. So you have a 5. The probability is 5 over 364 to get those 3 marbles in that order. Yep, you would do it every day. You could do it every day. And how many days during that year do you have the probability of drawing that? 5 of them. Yeah, plus 1 day. But October 22nd doesn't matter anyway. I don't know. I don't know. Just a random date.